Hi, I'm Amy from the Alt Store. Thank you for watching our video series. This video is called Wiring Your Solar System. If you missed our previous videos, I recommend you go back and watch the earlier ones in the series to get a good foundation, as they discuss the individual components. As we move further through the series, we're going to be getting deeper into the nitty-gritty. This video will discuss the considerations for wiring your system, including type and size of wire. Most of the requirements come from the United States National Electric Codes. Other countries may have different requirements, but for our purposes, we're going to be referring to the US NEC code. Let's start with some of the wire types you'll likely encounter. So here are a few terms commonly used. The grounding conductor is the equipment grounding wire that goes to earth ground from the metal in the system. It must be either green, green with yellow stripes, or bare copper. The grounded conductor is a current carrying conductor that is intentionally grounded. That's usually the negative in a grounded DC system and neutral in the AC side. It must be either white or gray. I know people are used to seeing the negative wire as black in DC systems, but that is incorrect according to NEC. It should only be black in an ungrounded system. For a grounded system, it should be white or gray. The ungrounded conductor is a current carrying conductor that is not grounded. That is usually the positive in DC systems, and both the positive and negative in ungrounded DC systems, such as with a transformerless inverter. You are allowed to use any color except white, gray, green, or bare copper. In DC systems, you'll usually use red wire for the positive, and in ungrounded DC systems, the ungrounded negative can be black. In AC, it's the hot lines. Line 1 is black, line 2 is red, and in three-phase systems, line 3 is blue. So just a quick summary of the color codes in the US. Be sure to check with your local codes for other countries. It can be difficult to find wire larger than 4 gauge with insulation color other than black. So it is acceptable in NEC to mark the wire with UL-listed electrical tape or paint. It is also allowed for the sunlight-resistant PV source wires coming off the array to have the grounded conductor marked with white electrical tape or paint at all ends, as that wire is usually only available in black. The types of wire used varies based on which segment you're wiring. This is a sampling of wires commonly used in PV systems. To go from the panels to a combiner box or pass-through box, you can use USE2 or PV wire. Both are sunlight resistant and can be used in wet or dry locations, as well as rated for 90 degrees Celsius. USE2 wire cannot be used in conduit unless it is also marked RHW2 or XHHW2. PV wire must be used in ungrounded systems, like those used in transformerless inverters, as it has a thicker insulation than the USE2. THWN2 and XHHW2 are typically used in conduit from the combiner box or pass-through box into the DC load center or DC disconnect of the inverter. It's not UV resistant and must be in conduit. THW is for dry locations only, and it's generally used for the battery to inverter cables. Most solar panels come with a sealed junction box with a few feet of cable and a watertight connector already attached to the back. These are great for wiring the panels in series. But to get the final home run from the connector to the combiner box or pass-through, you would generally get an extension cable that has a male and female connector on the ends. There are several different manufacturers of that connector. Try to match the manufacturer of the panel and the extension cable. Sometimes it isn't possible to get the exact manufacturer. Several panel datasheets simply say MC4 compatible, in which case you would just order an MC4 connector cable. Order it long enough to do both the plus and minus run, and cut it into 2 to provide both wires. Be sure to label the wire with tape to keep track of which wire is which once it goes back to the combiner box. Remember, red is for plus, white is for minus. Now we're going to get deeper into the NEC codebook. I hope you're sitting down. This is going to get interesting. I'll go slowly, but you may need to review the video a few times and take notes, as there are a lot of steps. All right, here we go. When designing your PV system in the US, you must comply with NEC. There are 4 considerations for wire size. 3 of them are covered with NEC. Believe it or not, voltage drop, the most commonly known wire sizing consideration, is not covered in NEC. Ampacity, the size and conduit fill, and temperature are all covered in detail in NEC. Let's start with them. After that, we'll go over voltage drop. Longer distances may require bigger wire than is required by NEC. Let's go over them one at a time. NEC's Table 310.15b16. Get used to it. You're going to be seeing it a lot. It tells you the allowable ampacity, or how much current it can carry at 30 degrees C. For example, 8-gauge RHW wire can carry up to 50 amps at 30 degrees C. If you don't see your wire type listed, use the temperature rating for that wire in the column as your guide. Table 310.15b2a covers the temperature correction for temperatures over 30 degrees C from the previous table. For example, if the ambient temperature is in fact 30 degrees C, it has a correction factor of 1. In other words, no change. But if the ambient temperature is 45 degrees, the correction for 75-degree wire is 0.82. So if the ampacity of the wire is 20 amps at 30 degrees, it can only handle 20 amps times 0.82 equals 16.4 amps at 45 degrees. And it gets even better. 2 more adjustments you need to make for heat are the distance the conduit is off the roof with Table 310.15b3c and the number of conductors in the conduit with Table 310.15b3a. The closer the conduit is to the roof, the hotter it gets in there, and the more conductors in that conduit, the more heat being dissipated from the wire, and so the hotter it gets. If you have less than 4 wires in conduit, you don't need to adjust for conduit fill, just for the conduit or cables in sunlight. Before we go any further, let's take a look at the schematic of this system. We have the 2 separate arrays, each with 2 strings of 3 going into the combiner box. The wire going into the combiner box is referred to as the PV source circuits. The combined output of the combiner box going into conduit is referred to as the PV output circuit. If this was not a combiner box and was just a pass-through box, not combining but just transitioning into conduit, the output wires would still be called the PV source circuit. The PV output circuit is going into conduit to the DC load center or breaker box. It's going to go through the breakers into the 2 charge controllers. It then goes through another set of breakers to the battery bank in conduit. It goes through yet another breaker to the inverter, also in conduit. And finally, it leaves the inverter as AC in EMT or LNFC to the AC breaker box. Okay, let's get started. First, for the PV source wire, we figure out the maximum circuit current of each string. We take the short circuit current of the panel, which is 9.09 amps, and multiply it by 1.25 for conditions where the sunlight may be brighter than standard test conditions. This is called over-irradiance. We then multiply it by another 1.25 for 3-hour continuous use. A shortcut would be to multiply the short circuit current by 1.56, which is 1.25 times 1.25. This brings us to 14.2 amps. Since this is a grounded system, I'm going to use USC2 wire from the panels to the combiner box. I checked the specs of the breaker that I'm going into in the combiner box, and the terminals are rated for up to 75 degrees C. So even though my USC2 wire is rated for 90 degrees C, I need to use a 75-degree column in my tables to meet the breaker requirements. The breaker is able to handle wire from 18 to 6 gauge, so let's keep that in mind. And remember, the ambient temperature that we're using is 38 degrees C. Since this PV source wire is not in conduit, and is generally shaded behind the panels, we don't need to worry about any temperature or conduit fill adders. So we take the 75 degrees C column, because that's the temperature rating of the breaker that the wire is connected to, and go to 38 degrees C ambient temperature and get a correction of 0.88. The continuous current we just calculated at 14.2 is divided by 0.88 to get a corrected current of 16.1 amps. Knowing we have to find the right size wire for 16.1 amps, we go to NEC's table 31015B16. We then go to the 75 degree row for wire and see that a minimum of 14 gauge wire is needed to handle 16.1 amps, since its ampacity of 20 is higher than 16 amps. I can use bigger than 14 gauge, which I will, because my extension cables are available in 10 gauge, but I can't go smaller than 14 gauge. We can confirm the breaker size that I chose is also appropriate for that wire. The 9.09 amp short circuit current times 1.56 equals 14.1 amps. So I'm using a 15 amp breaker, which is smaller than the ampacity of 20 amps for the breaker. So the breaker will trip before the current gets too high for that cable. Excellent. On to the PV output wire. The PV output circuit is the wire coming out of the combiner box to the DC load center. The combiner box is combining my two strings in parallel. So my 9.09 times 1.56 continuous current gets multiplied by two strings, which gives me 28.4 amps continuous current for the PV output wire. Because the wire will be in conduit coming out of the combiner box, I don't need to use UV resistant wire, so I can use the less expensive THWN2 wire. I'm running two sets of two current carrying conductors, the plus and minus for each of my two charge controllers, totaling 4 current carrying wires in conduit across the roof, with an ambient temperature of 38 degrees C. I'm using that same style breaker as in the combiner box, but a 30 amp instead of 15 amp, since it will have twice the current because the two strings are combined. So the temperature and wire size limitations are the same, 75 degrees C and up to 6 gauge wire. Because these 4 current carrying conductors plus the ground are going into conduit, table 31015B3A says I have to decrease the ampacity rating of the wire to 80% of its listed value, since it will get hotter than the 30 degrees C inside the conduit with all these wires. I can divide the continuous current of the PV source wire by 80%, bringing my current requirement up to 35.5 amps. Table 310.15B3C says that because the closer the conduit is to the roof, the hotter it gets in there. If I run the conduit right along the shingles, I have to add 33 degrees C to my ambient temperature to get a total of 71 degrees. I take this to NEC's table 31015B2A and see what temperature correction I have to use to reduce the ampacity of the wire. However, I see that the 75 degrees C column that I can't do 71 degrees because it's too close to my 75 degree limit. I have to figure out a way to reduce the temperature inside the conduit. Luckily, I see that by raising the conduit at least a half an inch off the roof, the resulting airflow will drop the temperature to just a 22 degree adder, getting me within the 75 degrees C acceptable range. So now we take our 38 degrees ambient plus 22 degrees conduit fill equals 58 degrees Celsius. That is within the capability of the 75 degree column. However, at this temperature, we reduce the ampacity of the wire by 0.58. Again, I can divide the current on the PV output wire by 0.58, bringing me up to 61.2 ampacity required on my wire. Whew, it's amazing what temperature compensation does to my requirements. So I go to the 75 degree column and find the smallest wire that can handle my new adjusted number of 61.2 amps. That brings me to 6-gauge wire. I do remember that my breaker can handle up to 6-gauge wire, so I'm good there. My breaker's a 30 amp breaker, which is less than 65 amps, so I'm good there too. But before I start doing the dance of joy, I have one more thing to check. I need to ensure that the voltage drop across my 50-foot span between the combiner box and the DC load center won't be greater than 2%. There are ways to calculate out the voltage drop, but for your sake and mine, I recommend you just go to one of the many voltage drop calculators available online. I used the one on rapidtables.com for this. Using the IMP of the panels times 2 strings in parallel, I get 16.78 amps. I have 3 panels in series, so the VMP times 3 equals 91.2 volts. I see the results of this calculator tells me that I'm less than 1% voltage drop with the 6-gauge wire. So now I can do the dance of joy. Okay, now that the dancing's done, let's move on to the battery cables. I know that I've got a 24 volt 3500 watt inverter, so 3500 watts divided by 20 volts, which is the lowest voltage that this inverter will work before it turns itself off, gives me 175 amps. This should be a lot easier because I only have 2 wires in conduit inside, so not in the sunlight. I can use THW wire since it's in a dry location. Let me check if I have to make any temperature adjustments. Because the room the equipment is in is a cool 22 degrees Celsius or 70 degrees Fahrenheit, my temperature adjustment is actually in my favor. I can divide the inverter's 175 amp by 1.05, decreasing the amount of current I need to plan for since the room is cooler than the 30 degrees it's rated at. I have only 2 wires in the conduit, so I don't need to factor in conduit fill, and it is inside, so not in the sun, so I don't have to worry about the hot conduit. This is going to be a piece of cake. I go to my favorite table, 31015B16, and look in the column for THW wire at 75 degrees C and see what size wire can handle 166 amps. 2-aught cable can do up to 175 amps. We have a winner. Another way of looking at this is to take the ampacity of the 2-aught wire and multiply it by my temperature adjustment of 1.05. That tells me that the wire in a 22 degrees C room can handle up to 183 amps. Since my inverter input was 175 amps, it is less than the adjusted 183 amps, so again, the 2-aught cable is fine. I'm going to check that the voltage drop of 10 feet of the 2-aught cable is less than 2%, and using my online calculator, I see that I'm at 1.4% drop. Perfect. That does it for the DC wires. It's getting easier with each step. Let's figure out the AC wires now. Again, it's in a cool 22 degrees C room, just going from the output of the inverter to the AC breaker panel. The specs for my inverter state that the continuous AC current is 29.2 amps. If I didn't have the specs, I could calculate it myself. It's a 3500 watt inverter divided by 120 volts AC equals 29.16 amps. Just like the specs said. I'm going to check with my tables and see what adjustments I need to do. Just like with a battery to inverter cable, because the room the equipment is in is a cool 22 degrees C, my temperature adjustment's in my favor. I can divide the 29.2 amps by 1.05, decreasing the amount of current I need to plan for, since the room is cooler than the 30 degrees it's rated at. I have less than 3 current carrying conductors. I've got line 1, neutral, and ground in the conduit, so I don't have to figure in conduit fill. And it's inside, so not in the sun, so again, I don't need to worry about hot conduit. Back to our friend table 31015B16 and look at the column for 75 degrees C and see what size wire can handle 27.8 amps. 10 gauge wire can do up to 35 amps, so we've got a winner. Plus, I checked in the install manual for that inverter and it recommended at least 10 gauge wire. So there you go. Now let's review what we came up with. Our PV source wire coming off the panels only required 14 gauge wire, but we increased it to 10 gauge as that was what was available in the USE2 extension cables. We're going to mark the negative with white electrical tape since it was only available in black cable. Our PV output wires from the combiner box in Conduit to the DC load center was 6 gauge THWN2. The 2 positive wires are red, 2 negatives are white, and the ground is green. The battery to inverter cables are 2-aught THW cable. The negative cable is marked with paint or electrical tape as white, and I've got a red cable for the positive. Then the AC output of the inverter is 10 gauge, black for line 1, white for neutral, and green or bare for ground. I don't know about you, but that's enough for me for now. To get you started for your house, the Alti store's got a bunch of calculators available to help determine what size system you need. We also have many other package systems that we've already designed as a starting point, allowing you to customize them for your particular needs. Check out more of our video series on our website. We've got a team of highly trained technical sales reps available to help you plan your system. Give us a call. And don't forget to check out the rest of our website at altistore.com, where we are making renewable doable.